Now that we have some idea of what we are trying to do with data and models, in order to estimate the parameters of the chosen model, we will try to get into some mathematical details using this first case study. So here is the same example that we looked at in one of the earlier videos. We have 7 data pairs x comma y. That means you have a system where x is the input and y is the output, and the experimenter changes the settings of x and obtains readings of y corresponding to that value of x. So for the first sample x1, the value of x is equal to 1, and the corresponding value of y that was obtained is y1, which is equal to a numerical value of 0.5. The third experiment was done at x is equal to 3, so x3 is equal to 3. So when I say x3, it means the value of x in the third experiment. And the corresponding value of y, which is labeled as y3 in this example, and the numerical value of y3 equals 2, etc. So we have 7 samples or 7 data points in this particular case. And looking at the data trend, the modeler and the experimenter feel that you could fit a straight line to the data. So the proposed model is y is equal to a naught plus a1x plus e. So e is basically the error that is associated with the model. It contains all our ignorance and mistakes in our model and experiments together. Now, a naught represents the intercept and a1 represents the slope of this line that we are fitting through this data point. So the model equation is y is equal to a naught plus a1x plus e, and you can refer to it as the master equation, because we would expect that every experimental point, the 7 experimental points, each of those 7 experimental points will obey this relationship, which is given by this model equation or master equation. So all the 7 observations will have the same a naught value and the same a1 value because they come from the same system. What is different between these 7 samples is the value of x that we use, the value of y we obtain, and the value of the error that could be there. But a0 and a1 are the same for all these 7 observations. And we are basically trying to find out what this a0 and what this a1 is. Using subscript I for the sample number, the master equation that is customized for sample I becomes this. This is the master equation, as you can see, and when you customize it for sample I, it becomes this. yi is equal to a0 plus a1 times xi plus ei. Xi can be different for each experimental point, and consequently yi can be different for different experimental points, and because of this the error for experiment I can be different from that of the other experiments. Please note that I have not used A0i and A1i because we assume that for all experiments done on the system and which we have the data for, the value of A0 and A1 is going to be fixed. What changes from experiment to experiment are the input values, the corresponding output value, and consequently the errors that are associated with each experiment. So we use the subscripts I for symbols y, x, and e only. And I denotes the sample number here. So for sample 1, we can write the master equation as y1 is equal to a0 plus a1 x1 plus e1. x1 is the value of x associated with the first experiment. In this case, x1 is equal to 1. And the value of y that is obtained is y1, which has got a value of 0.5 in this data set. So x1 is equal to 1, y1 is equal to 0.5, and I do not know what is the error in the first experiment. I will just leave it as E1. Now, when you come to the second sample point, I will write y2, 2 indicating it's for the second sample. I am writing the master equation for the second sample in particular. So y2 is equal to a0 plus a1 x2 plus e2. x2 has a numerical value of 2 here, and y2 has a numerical value of 2.5. So we know x2 and y2. We concede there is going to be an error which we denote by the symbol E2, but we do not know what it is. So if you continue this process, you can write these equations for experiments 3, 4, 5, 6, and 7. So for experiment 7, the master equation reduces to, or can be written customized for the seventh sample as y7 is equal to a0 plus a1 x7 plus e7, where x7 is 7 and y7 is 5.5. So let's look at the overall idea so far. We have the data, we have hypothesized this model, and therefore we write this as the model equation or the master equation. And we said for sample I, this master equation can be customized for each sample. Sample 1 to sample 7 in this particular case. So once we recognize that, we are able to write these 7 equations. Once we write these 7 equations, we readily recognize that it can be put in a vector matrix form. So on the left hand side, I'm going to collect all the y values and stack them up in this particular fashion to create a column vector containing the values of y1 to y7. So this is called the y vector. Now this should be an equal to sign. Pardon me for that typo. And the right hand side can be written as 1 x1, 1 x2, 1 x3 all the way till 1 x7 multiplied by a0 a1. And as you can see, 1 multiplied by a0 will be a0 plus x1 multiplied by a1 will be a1 x1. So if you look at the right hand side for the first equation, it will be 1 times a0 plus x1 times a1, which is a0 plus a1 x1, which is what you see here. If you look at the second row, 1 multiplies with a0 plus x2 multiplies with a1 to give us a0 plus a1 x2, which is what you see on the right hand side for sample 2. Likewise for sample 7, it is going to be 1 times a0 plus a1 times x7, which is what you see here. So you have this matrix which I call as X, which contains a column of ones. So this is a column of ones. As you can see, there are only ones in this column, and that column is required so that we can estimate the value of a0. And then you have a column containing the X values for experiments 1 to 7 in that order. That column is used to estimate a1 plus, and now we can stack up the errors e1, e2, e3, e4 till e7 in this particular way. I've used epsilon here, but you can understand that e1 is equal to epsilon 1, e2 is equal to epsilon 2, etc. So you have the error vector here. So if you take the overall thing, y1 is equal to 1 times a0 plus x1 times a1 plus e1 or epsilon 1. That gives us the first equation. So if you take the fifth sample, y5 is equal to 1 times a0 plus x5 times a1 plus e5, which gives us this particular equation. So we have faithfully represented the master equation for every data sample here, and we have put this 7 equations in matrix vector form. Kindly remember to replace this plus sign by an equal to sign. That was a mistake on my part. So at this point in time, this is the most important thing. I can represent this data modeling problem as y is equal to x beta plus epsilon. This is y, this vector is y, this matrix is x, this is the unknown vector beta, and this is the error vector epsilon. So y is equal to x beta plus epsilon. In this particular case, we know y and x, because once you have done the experiments, you know y1 to y7. You would also know x1 to x7. And anyway, this is a column of ones. So the x matrix is known. So the y vector is known, the x matrix is known, the unknown vector is beta. This is the parameter vector, and we are trying to find out what beta is. Because if we know what beta is, then we know a0 and a1, and therefore our parameter estimation problem is completed. Of course, the error is unknown. So the error vector is also unknown, but we know some of its properties. As I said, I'm not going to go into those properties, but some of the properties include, as I said in an earlier video, epsilon vector, right? The errors E1 to E7 comes from a normal distribution with mean 0 and constant variance. We also assume that E1, E2, E3, E4, E5, E6, E7 are independent of each other, etc. So under those assumptions, we can still make progress. Because this equation is one equation, right? But it has two unknowns. Beta is unknown, epsilon is unknown. So it might seem to be a case of a situation where we cannot determine two things, right? You have, one equation. How can we determine two unknowns from that? But the point is, we assume that the sum of the properties of epsilon are known, and therefore we can back out beta based on those assumptions, and as long as those assumptions are valid. Anyway, as of now, we can say every linear regression problem can be converted or put in this particular form. Y is equal to x beta plus e or epsilon. And beta is the unknown. X and y are known once you have completed the experiments. Now comes some mathematics that I hope you will take it in slowly but surely. So this is the equation. Y is equal to x beta plus epsilon. This is exactly what we wrote in the previous slide. So I can take this x beta to the left side and I will have y minus x beta is equal to epsilon. Or I can write it as epsilon is equal to y minus x beta. And I can also write y minus x beta as y minus y hat, where y hat is equal to x beta. Y represents the experimentally obtained data points, the values of the measurements of the output. So that is y. Y hat is the value of y predicted by the model, right? Because the model has parameters beta, and if you know x and you know beta, you can multiply x and beta to get the signal part of y. And therefore y hat is equal to x beta is the value of y predicted by the model. Of course, we would like the values predicted by the model to be exactly the same as that of the experimental values. But we know because the y measurements contain noise, that is not a good thing. We would like y hat to be as close as possible to y, but we are always afraid if we fit y exactly because we may be fitting noise. We would like y minus y hat and therefore epsilon to be small. We necessarily do not want epsilon to be 0. So where we are now is epsilon is equal to y minus x beta, and x beta can be written as y hat. So just focus on epsilon is equal to y minus x beta. And now let's look at the dimensions of each of those entities that are there. Epsilon is going to be n by 1, where n is the number of samples in your data set. Now if you look at the example that we have, n is equal to 7 because we have 7 data points here or 7 samples here. So epsilon is 7 by 1, 7 rows and 1 column. So epsilon is in general n by 1. In this example it is 7 by 1. The y vector is also n by 1 as you can see here. N is 7, therefore y vector is 7 by 1. So y vector is n by 1 in general. Now this X matrix is n by p. It has n rows and p columns, where p is the number of parameters in the model. In our example, we have 7 sample points or 7 data points, and the number of parameters is 2. The parameters are a0 and a1. Therefore, X in our example is 7 by 2, as you can see here. 7 rows, row 1, row 2, row 3, all the way till row 7, and then you have 2 columns, column 1 and column 2. So in our case, we know that X is 7 by 2, and in the more general case, X will be n by p. N rows, each row corresponding to one sample, and p columns, with each column helping out in the determination of one of the parameters in the model. And beta is p by 1. In our case, p is 2, so beta should be 2 by 1, as is the case here. Because beta is 2 by 1, 2 rows and 1 column, you understand that beta is a column vector, and it has 2 rows in this particular case, because in our model, the parameters are 2 in number, a0 and a1. In general, you can have a model with p parameters, and beta will be of size p by 1. That also works well for us because x should multiply with beta in a compatible way. So x is n by p, and beta is p by 1. So the number of columns of the first entity should be equal to the number of rows of the second entity for the multiplication to be possible. So n by p multiplies with p by 1 to give you n by 1, which is great because the dimensions of y and epsilon are n by 1. So everything works out neatly. Now comes another important idea. If epsilon is y minus x beta, epsilon transpose will be y minus x beta transpose, right? So I'm transposing the left hand side and the right hand side. So this is okay. Now, if you expand the right hand side, you're going to get y transpose from the first term minus x beta transpose. And from matrix algebra, you know that AB transpose, where A and B are matrices, AB transpose will be B transpose A transpose. Using that result, epsilon transpose is going to be Y transpose minus X beta transpose will be beta transpose X transpose, using this basic idea from matrix algebra. So epsilon transpose is Y transpose minus beta transpose X transpose. And if you look at the dimensions, because epsilon is n by 1, epsilon transpose will be 1 by n, because the column vector will become a row vector when you transpose it. So it's not surprising that epsilon transpose is 1 by n. And on the right hand side, y transpose is also going to be 1 by n, because y is n by 1. Therefore, y transpose will be 1 by n minus beta transpose. If beta is p by 1, beta transpose will be 1 by p. And x is n by p, therefore x transpose will be p by n. So 1 times p multiplies with p by n. That's okay because this is compatible. The number of columns of the first entity matches the number of rows of the second entity. So multiplication is okay. And the result is going to be 1 by n. So every term here in this equation is of size 1 by n. So everything works out well. So far what we have achieved is we have got expressions for epsilon as y minus x beta, and all the entities here, this and this, is of size n by 1. Each of those three entities is of size n by 1. So epsilon is of size n by 1. Epsilon transpose, which is y transpose minus beta transpose x transpose, this epsilon transpose is of size 1 by n. And each entity in this equation is of size 1 by n. We saw that. Now, let us write for our example, right? What was epsilon? Epsilon is epsilon 1, epsilon 2, all the way till epsilon 7. This is epsilon for us in our example. And what is epsilon transpose? Epsilon transpose is going to be E1, E2, all the way till epsilon 7, right? This is epsilon transpose, 1 by 7. This is epsilon, which is 7 by 1. So epsilon transpose epsilon, if you multiply epsilon transpose with epsilon, epsilon transpose epsilon is going to be 1 by 7 multiplied with 7 by 1. So the result is going to be 1 by 7 multiplies with 7 by 1 to give you a 1 by 1 entity. So epsilon transpose epsilon is a 1 by 1. That means epsilon transpose epsilon is a scalar quantity. Scalar, that means it's a single number. Epsilon is a vector, epsilon transpose is a vector. Specifically, epsilon is a column vector, epsilon transpose is a row vector. So row vector multiplied by a column vector is going to give you a scalar quantity. It is going to result in one single number. So epsilon transpose epsilon is a number. And what if you transpose a number? You will get back the number. The transpose of 5 is 5 transpose, which is also 5. There's nothing to rotate about a scalar quantity, right? So that is one interesting idea. And what exactly will this epsilon transpose epsilon be? Epsilon transpose epsilon will be E1 multiplied by E1, or epsilon 1 multiplied by epsilon 1 plus epsilon 2 multiplied by epsilon 2 plus epsilon 3 multiplied by epsilon 3 all the way till plus epsilon 7 multiplied by epsilon 7. So that is going to be equal to epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared all the way till plus epsilon 7 squared. In general, it will be epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared plus epsilon 4 squared all the way till epsilon n squared, where n is the number of samples. So this is what you see in the general case. And I can denote it by the symbol j. J is a number. And what is the physical interpretation of j? The physical interpretation of j is j represents the sum of squared errors. So the model has an error term and every observation has an associated error term. So when you square up all those observation errors and you add it up, you will get sum of squared errors. So J is nothing but what is sometimes referred as SSE, sum of squared errors. So what I would like to do is I would like to minimize this J. That means I would like to minimize epsilon transpose epsilon or sum of squared errors in the model. I would like to minimize that. In fact, I would like that to be 0 while taking care to see that there is no overfitting. So the question is, what can we change in the model now? You cannot change Y because you have done experiments and you have got values for Y. So if you change Y, it means you're doctoring the data, which is ethically wrong. You're not a scientist anymore if you do that. Similarly, you cannot change this X matrix. So once you have done the experiments and the model is fixed, then you cannot change X. So Y and X cannot be changed. You can use them, but you cannot change them. So the only thing that is at your hand as a lever to make J small is beta. So the problem is to find a beta, to find out values of A0 and A1 in this example such that epsilon transpose epsilon, that is J, becomes minimum. This is an optimization problem. So find the optimal value of beta such that J equals epsilon transpose epsilon is the smallest. So that is why it is called a least squares problem, because we are minimizing. The word least means we are trying to minimize. And what are we trying to minimize? We are trying to minimize sum of squares. So least squares, minimize sum of squares. All right, so this is called a least squares problem. Fortunately for this case, under these assumptions, we have an analytical solution. In shorthand, we might just write it as minimize epsilon transpose epsilon using betas as the decision variables. We are free to find out the best values of beta such that this measure gets minimized. In other notation, you can write it as minimize J by using beta as the handles or using beta as the decision variables. Okay, so conceptually, we have expressions for epsilon transpose epsilon. We know it is going to be equal to the sum of squared errors, which we denote by the symbol J, and we have set our goal to minimize the value of J by an appropriate choice of beta. Now, let's proceed further. I can now write epsilon transpose epsilon using the original symbols Y, X, beta, etc. So we know epsilon transpose is this. We have written it earlier. And epsilon is this. So epsilon transpose epsilon is this entity multiplied with this entity. This is a row vector and this is a column vector. And we know epsilon transpose epsilon, we have called it as J. So now what I do next is I say J, which is equal to epsilon transpose epsilon, equals, I now expand the expression here. So Y transpose multiplied by Y, so that is Y transpose Y. Then minus, so I have a minus here. Beta transpose X transpose Y. So beta transpose X transpose multiplies with this Y and along with this minus sign to give us this. Then Y transpose multiplies with this minus X beta term to give us minus Y transpose X beta. And then minus beta transpose X transpose multiplies with minus X beta to give us plus beta transpose X transpose X beta. So you should know by now the origin of these four terms that you see on the right hand side. That comes from expansion of this multiplication. And because epsilon transpose epsilon and j are scalars, we have already seen it, right? And therefore each entity here must be a scalar. Y transpose y will be 1 by 1. Beta transpose x transpose y will be a 1 by 1 dimension entity. Y transpose x beta will be 1 by 1. Beta transpose x beta will also be 1 by 1. Though they look, formidable and scary, each of them is pretty harmless scalar quantity. This is a scalar quantity, this is scalar, this is scalar, this is scalar. And the interesting idea is the transpose of a scalar is the same scalar. All right, so this is an idea that I already mentioned. I also mention it again here. So at this point, we know that j, which is the objective function that we want to minimize, can be written in this particular way as the addition subtraction of 4 scalar entities. And we are not at liberty to change y and x because those come from experimental data, and it is illegal and unethical to change the data once it has been collected. So the only way in which you can minimize j is by our choice of beta, because the model is our choice. All right, so we can change beta any way we want, and here we have chosen beta to contain a0 and a1. Therefore the question is, what are the best values of a0 and a1 that will take this model go as close as possible to the experimental values of y, therefore minimizing j. So j is this, as we wrote in the previous slide, and I've said here that this and this, right, are exactly the same. Why? Because each of them is a scalar quantity, and we said transpose of a scalar is the scalar itself. So if I take y transpose x beta, which is this term, let's say I transpose it. So this is a scalar quantity, and transpose of it should be the same. So y transpose x beta transpose should be the same as y transpose x beta. But we also know from matrix algebra that y transpose x beta, the whole transpose, should be equal to beta transpose x transpose y transpose transpose, which will be y, because transpose of a transpose will give you the original symbol. Therefore this should be the same as this. This and this are the same. So wherever I see y transpose x beta, I can replace it with its transpose, which is beta transpose x transpose y. So this term can be replaced by beta transpose x transpose y because they are the same. And therefore, instead of writing it as two terms that look different, I can write it as y transpose y, this term, minus 2 beta transpose x transpose y, because this is minus beta transpose x transpose y. This is minus y transpose x beta, which can be written as minus beta transpose x transpose y. Therefore, this two terms put together, we can write it like this. And then we have the last term, which is plus beta transpose x beta. So at this point in time, I can write j is equal to y transpose y minus 2 beta transpose x transpose y plus beta transpose x beta. We learned in high school that to find out the maxima and minima of functions, let's say we had a function of x, right? To find out its minima or maxima, we would take df by dx and set it equal to 0. Then we will get some x values, and then what we can do is we can take the second derivative and look at the sign of the second derivative at the values of x you found out by equating the derivative equal to 0. That will tell us whether it's a maxima or minima or saddle point, etc. Likewise, I want to find out the minima of this function j, and the unknown here is beta. So what I'm going to do is I'm going to take the partial of j with respect to beta, or the derivative of j with respect to beta. When I do that, I will get dou j by dou beta is going to be this y transpose y term, right? This y transpose y term does not involve beta. So the contribution of that to the derivative will be 0. And when you come to the second term, this minus is a minus here. And if you look at multivariable calculus, we can show that this term, when you take the derivative with respect to beta, is going to give you 2x transpose y. All right, so that is what you see here. And the derivative of the last term with respect to beta is going to be 2 times x transpose x beta. That is what you see here. This comes from multivariable calculus. So it's something like this. Let's say f is 2x y squared z. Let's just pretend, right? F is 2x y squared z. What is dou f by dou x? That's going to be 2y squared z. Likewise, if the function is 2 beta transpose x transpose y, and you're taking the derivative of that with respect to beta, you're going to knock off this beta kind of term, like you knocked out the x term from here to get the value of the partial derivative in this particular example. So you just knock off this and you get 2y squared z to be the derivative. Likewise, if you take this term, second term, and you're trying to find out the partial derivative of that with respect to beta, this beta term gets knocked off, you will get just 2x transpose y. So that is how you get this. Now suppose your function is x squared y z, and you want to find out dou f by dou x. So what would that be? You will retain this y z, and the derivative of x squared with respect to x will be 2x. Likewise, this beta x transpose x beta, this beta transpose beta is something like x squared. So if you take the derivative of x squared with respect to x, you're getting 2x. Likewise, if you take the derivative of this term with respect to beta, you will get 2 times beta. So it should not be surprising that you get this to be the derivative of this term with respect to beta. Of course, you have to take a multivariable calculus textbook and do this rigorously. I'm just trying to give you a flavor for how we can compute the partial derivatives of the terms in J. So if you take this to be J, this will be dou J by dou beta. And for a maxima or minima, we set the first derivative equal to 0. So dou J by dou beta is set equal to 0, which means minus 2x transpose y plus 2x transpose x beta is equal to 0. So I can take this minus 2x transpose y to the right hand side. Therefore, the left hand side will be 2x transpose x beta equals, and the right hand side will now be 2x transpose y. And I can cancel out this 2 on both sides, and I will get x transpose x beta is x transpose y. So from here, how do you get beta? So what we do is we pre-multiply both sides by x transpose x inverse. So the left hand side will be x transpose x inverse, x transpose x beta, and the right hand side will be x transpose x inverse, x transpose y. So this is a very legal operation, because we are pre-multiplying both sides by the same entity, x transpose x inverse. So x transpose x inverse, x transpose x, this is like multiplying a matrix by its inverse. So this is going to give you the identity matrix, which is like 1. So the left hand side will just be beta. The right hand side will be x transpose x inverse, x transpose y. So this is the solution for beta. And now in this particular example, beta will contain two values. The first value will be a0, the second value will be a1. And this is the calculation that goes behind polyfit and similar commands that estimate linear regression models. Kindly note that there is a typo here. There should be no beta here. So this should just be beta is equal to x transpose x inverse x transpose y. Sometimes we put the subscript ls for beta to say it's the least squares estimate. Okay, because if you choose a different objective function, you will get a different answer for beta. So the parameter estimates that we get depends on what objective we choose. Here we chosen to minimize the sum of squared errors. So we have looked for least squared error, if you like. So it's called least squares. So beta ls is equal to x transpose x inverse x transpose y. Now if you take the second derivative of j with respect to beta, we will get dou squared j by dou beta squared. So if you take this and you take the derivative of that with respect to beta, this term will contribute 0 because it doesn't contain any beta. This term would contribute 2x transpose x. And 2x transpose x is like a positive quantity because this is a positive definite matrix, etc. So that goes a little beyond the scope of this course. But please understand this is equivalent to a positive number when we work with scalar functions. Here we are working with vectors, right, and matrices, so it's slightly different. So this x transpose x matrix is called a positive definite matrix. So it is like a positive number. And when the second derivative is positive, we know that we have located a minima. So this beta, which is equal to x transpose x inverse x transpose y, gives the minimum value for the function j. That is what is written here. Beta least squares gives us the minima. Please note that you will not be asked for derivation of these kinds of things. That's not the intention of teaching this to you. The intention of teaching this is to say what is underneath functions like polyfit and stepwise and things like that. So there is clear mathematics underneath it. There is a lot of rigor underneath what you see as built-in MATLAB functions. If somebody asks you what is linear regression, you should be able to say something more than, oh, it is a polyfit function in MATLAB or it is a stepwise function in MATLAB. No, these are just implementations in MATLAB. What is behind linear regression are the assumptions about the noise that I talked about. What is underneath linear regression is the objective function that we choose. And it is the mechanism by which we get the expression for beta. These are things that you should be able to talk about. Though nobody may ask you to derive the expression for beta, but you must understand the process, the logical mechanism by which these formulae have been computed. And this least squares is the very important machinery for all the parameter estimation problems that we see. Thus, it is very important for you to at least appreciate these things once and then move on with MATLAB implementations, etc. Now, finally, let us see how we can solve this problem in MATLAB. I'm going to make use of the polyfit function, which has already been described to you. What this video is about is what is underneath polyfit that gives us these answers. Now, if you look at this lsqfitdemo.m function that I've shared with you, you will see this code. And this code is very easy to interpret. I will do it once for us. So I say clear all, close all in the first line of my MATLAB M file to make sure that all variables that are currently in the workspace are cleared and all the figure windows that are open, all of them are closed. Then I input the data, the x data and the y data as column vectors. That is why you see the apostrophe sign here. So the x values luckily are 1, 2, 3, 4, 5, 6, 7. So instead of typing x is equal to 1, 2, 3 all the way till 7, I just chose to say and then put apostrophe here to make it a column vector. I just wanted to say that x is nothing but 1, start at 1 in steps of 1, go till 7 and stop, and then apostrophe to make it a column vector. And y, the y values, right, from the table. So 0.5, 2.5, 2, 4, 3.5, 6, 5.5, all with one blank in between each of the numbers with a blank in between the individual numbers, right? So that is y. Again, apostrophe to make y a column vector. Then I create the X matrix. As you know, the X matrix has a column of ones and then the X measurement column. So 1, 7, 1 will create this, right? 7 ones, right? 7 ones. And then this X will contain these values 1, 2, 3, 4, 5, 6, 7. So now this big X matrix will contain a column of ones and a column with X measurements. And then we know beta is equal to inverse of x transpose x. So this is x transpose x inverse times x transpose times y. So this is the beta that we just determined, right? So I'm just implementing that equation. Beta is equal to x transpose x inverse x transpose y. So in MATLAB, INV of x transpose x will create x transpose x inverse, and then I multiply it with x transpose and I multiply it with y in this particular order. So beta should contain the parameters a0 and a1. When this executes, MATLAB gives the values for the beta vector to be this. So 0.0714 is my a0 and 0.8393 is my a1 because of the way we have arranged the X matrix and the beta vector. The first element is a0, the second element is a1. So our estimate of the model right now is y is equal to a0, which is 0.0714 plus 0.8393, which is a1 times x. Plus, of course, we concede there could be errors in the model. So this is the model that we come up with. This is the signal part or the deterministic part. This is the noise part or the stochastic part. So this is the model we get from implementation of the formula we just derived. Now let's do the same thing using polyfit command in MATLAB, because you have been introduced to that already, right? In the course opening videos of the course, we saw how we can fit polynomials to data. Here we are going to fit a first order polynomial because we are interested in fitting a line. So p comma s is equal to polyfit x comma y comma 1, the independent variable measurements. So x comes first, the dependent variable measurements y comes next, and the order of the polynomial we are trying to build comes as a third input argument. So the output is in p and s, with s containing the statistical information and p containing the values of the parameters, the coefficients of the polynomials. So P turns out to be 0.8393 and 0.0714. So the coefficient of the leading term, which is the highest order term in the polynomial, which is the x term here, is displayed first, and the constant term is displayed next. So in polyfit output, this is A1 and this is A0, which matches with what we had here. All right, so polyfit gives the coefficients of the polynomial, of the estimated polynomial, in a certain order. So this is the coefficient of x, this is the coefficient of x to the power of 0, that means it is the coefficient of the constant term. Whereas in the way we have designed our x matrix, the first element will be the constant term and the second element will be the slope term. And in doing this x matrix, I have followed the conventional literature. So don't think I've been crazy and I've done something that is not done in practice. In fact, the way we have arranged our beta and the X matrix is what is done in practice. So kindly understand that. Then what I want to do is, yes, we have got all these answers. I want to draw the best fit line. So what I've basically done is I've said, okay, X values, let us choose values going from 1 to 7, but in steps of 0.01. All right, so I get a fine, nice, smooth line, right? So I say that is X vals. And for each of these values in X vals, I'm calculating a value of y hat. This is the model predictions based on our values of beta 1, which is a naught, and our values of beta 2, which is a1. So beta 1 is a naught, beta 2 is a1, as we have noted previously. So a1, I will multiply the x values with that and add this a naught to it to get my predicted values of y. So when I calculate y hat and I plot the experimental points as red circles, and on the same plot using the hold on command, I plot the model predicted values for y for the x values in the same range from 1 to 7, though on a finer scale, I get this blue line to be the best fit line. And as you can see, it passes through the cloud of points, right? The idea is no other line will have the same low value of j. This is the line that will have the smallest value of sum of squared errors. No other line will have such a low sum of squared errors or such a low value of j. Any other line will have a higher value of j. Now please note this distance from the line to the data point, this is epsilon 1. This is epsilon 2. This height from the line to the data point, this is epsilon 3. This is epsilon 4. This is epsilon 5, this height. This is epsilon 6. This is epsilon 7, this gap. So this line minimizes epsilon 1 squared plus epsilon 2 squared all the way till plus epsilon 7 squared. So this line minimizes this measure. We don't minimize epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4 plus epsilon 5 plus epsilon 6 plus epsilon 7 simply because we do not want negative errors to compensate for positive errors. That is not good. We want to penalize both the negative errors and the positive errors in the same way. For example, here, right, epsilon 1 is negative. If you say epsilon is the experimental value minus the model value, epsilon 1 is negative, whereas epsilon 2 is positive. So we do not want this error to compensate for this error, right? Two errors do not make something right. So instead, we say we are going to look at the squared errors, right? Because squared errors are always positive, and we want to minimize the sum of squared errors, right? So that is the other idea behind this best fit line or the best fit curve or the best fit for polynomial, etc. So I'll stop this case study 1 here. We have covered a lot of ground. I will try to catch up with you in the next videos through other case studies. Thank you for your time.